Hello Precalc BC. We are going on to day 2 of chapter 3, and today we are talking about polynomial functions and models. So let's go ahead and get started. So what is a polynomial function, you may ask? Well, a polynomial function is a function in this form right here, and it's basically any of our equations that are like an x squared or an x cubed or an x to the fourth. They all represent smooth curves, which is called continuous, which we will get into much later. And the really big thing that we need to notice about them is they cannot have negative or fractional exponents. So if you have anything like that, we know we're not dealing with a polynomial function. And there are certain aspects of polynomial functions that we're going to discuss in this lesson today. One thing is the degree, and the degree of the polynomial function is represented by the highest exponent of the polynomial, and what that does is determine its shape and end behavior. End behavior meaning what it's doing at the ends of the graph. Is it going up? Is it going down? What is it doing? It's doing one of those two things. So if we look at x squared, which is a graph that you should be pretty familiar with. We're just going to draw a sketch of it. We want to look at that compared to x to the fourth. Okay, so here's my x squared. Oops, let's do a zoom 6. All right, and if I go ahead and I also put in an x to the fourth power, I'm going to notice it's the same general shape, but it's going to be a little steeper, and it's also a little flatter around the vertex there. So we can zoom in a little bit and you can see what I mean. See how it flattens out more instead of curving like the parabola? So I'm just going to have you go ahead and draw that picture. Okay, so I cheated. I literally just drew it, copied it from my calculator. So there you go, there's my beautiful graph. Now we're going to go ahead and do the same thing with the x cubed versus x to the fifth. Okay, and I'll do a zoom 6 again. So x cubed, we should have a pretty good idea of what that looks like. Okay, and now x to the fifth. Same sort of idea, okay? It's steeper, and it flattens out more right around the origin. So go ahead and draw a picture of that now for me. Okay, so I've cheated again. I've drawn it from my calculator again. So these two graphs, or actually 4 graphs, help us make some predictions that happen to be true about all polynomials based on their power. So the topics that we're going to discuss are symmetry, domain range, key points, and end or origin behavior. If you have an even integer for your power, for your exponent, for example, x squared, x to the fourth, x to the sixth, any of those, you have even symmetry, meaning you're symmetrical over the y-axis. All right, we can see that right here. Okay, we know that with the parabola. Your domain is all real numbers, and your range is 0 to infinity. Now, obviously, if you have some sort of shift, that 0 might not be the case, okay, or if there's a reflection, but at least for the original power function, okay, x squared, x to the fourth, x to the sixth, that would be your range. The other thing that's going to be true for all of these is that you have the following 3 key points. Okay, again, this is for the power functions. If you have some sort of shift or a reflection or a stretch or a compress, you're not necessarily going to have those points. But if you have any of these original power functions, x to the fourth, x squared, x to the sixth, you'll have those 3 points for every single one. What also happens is that between -1 and 1, it is flatter. Okay, we saw that with both of those graphs, and then as you move away from the origin, you're getting steeper. Okay, now certainly the x to the fourth is much steeper than x squared, but you can still see that it's getting steeper as it goes on. All right, and then for our end behavior, it's going the same direction. They're both going up. Okay, and even if it was reflected, they'd both be going down. our end behavior is going the same direction on either ends of our graph. Okay. Now, when you have an odd integer, so for example, x to the third, x to the fifth, x to the seventh, we have odd symmetry, okay, because we are symmetrical over the origin. We can see that in our picture. Your domain and range are both all real numbers, okay, and we can see that because think about an x cubed. It doesn't matter what number you put in, and you're always going to get either a positive or a negative out. So all real numbers. You have these three key points, and actually this is very similar from the origin behavior of our even integers. You're flatter between -1 and 1 right around the origin, and then outside of it you're steeper. The difference is the end behavior. The end behavior for these odd exponents, they're always going the opposite direction. Okay, where am I? There we go. One's going, oh gosh, this is hard to do in this little webcam. Okay, one's going up and one's going down. Okay, there was your haha for the day. So yes, end behavior going in different directions. All right, let's talk about zeros of a polynomial function. Whether a graph bounces or touches, okay, those are the same thing, or crosses through the x-axis depends on what's called multiplicity. Okay, now what is multiplicity? This is probably a new term for you. Even multiplicity means that you have an even exponent, so it is squared, okay, or to the fourth power. And when we have even multiplicity, we're going to bounce or touch the x-axis. Okay, and when we have an odd multiplicity, so raised to the first power, the third power, the fifth power, we're going to cross the x-axis. All right, so for example, based on this graph, we can write a general function. Okay, now there may be some a value in front that we don't know about, so I'm just going to put that here. But I can write this in factored form based on the zeros that I have. I have a 0 at -1, so that would be an x plus 1. But see how it bounces? That's going to mean this is a squared. Okay, now you may be asking, well, how do you know it's not to the fourth power? Hold on, I'll get there. And then we also have a 0 at 1. So it's going to be x minus 1, but it crosses. So this is going to remain to the first power. And then we have a 0 at 3. So it's going to be x minus 3. And again, it crosses, so this is going to be to the first power. Now, the reason you know it has to be a 2, 1, 1 is because of the overall degree of this polynomial. This is a W type shape, so this is something you should recognize as a degree 4. Okay, or an x to the fourth for your power function. And what that means is that all of your individual multiplicities have to add up to that total degree. So this has to be a 2, 1, 1 because that's the only way to add up to 4 by having an even number and then the two odds. Okay? All right, so let's practice this a little bit. We're going to form a polynomial in standard form whose zeros and degree are given. Okay, so here are our zeros. Make sure you have your f of x equals. And they tell us our overall degree. Okay, well look, since you have 3 zeros and your overall degree is 3, that means each of these zeros has to have a multiplicity of just 1. Okay, which would mean that this graph would be crossing at each of these places. Sorry, that was my dog. Today is garbage day. It's a very stressful day in the household for my dog. Penny is currently very traumatized by the garbage truck. It's just really traumatic. She doesn't care for it. So she needs to sit on my lap right now. All right, so this will be a challenge. Here we go. All right, so this is not going to go well. We are going to write this polynomial. We just said this is degree 3, and each of these zeros will have to have an individual multiplicity of 1. So if your 0 is -1, then we'll have an x plus 1, and that'll just be to the first power. if your 0 is 1, we'll have an x minus 1. Look, it's like a poodle is teaching your pre-calc lesson. And if you have a 0 of 3, then we'll have an x minus 3. Now, this is factored form, okay? But this problem requests standard form. So guess what you get to do with this now? Foil! All right, so let's go ahead and foil it. Okay, you got to get over the garbage truck. Get down. And we'll foil this out. Okay, and then you'll just keep on foiling. So that'll be an x cubed minus 3x squared minus 1x plus 3. And I think that looks good. Okay, and there you go. All right, let's try another one. We have zeros of -2, multiplicity 2, 4, multiplicity 1, and overall our degree is 3, which makes sense because a multiplicity of 1 plus 2 does equal to 3, because math. Okay, so let's give it a try. 0 of -2, that'll look like x plus 2. Make sure we square it because that's our multiplicity. A 0 of 4 becomes x minus 4, multiplicity of 1. Okay, so I'm just going to leave that. And then again, we do want standard form. So we'll FOIL this out. All right, and one method that I use that I find helpful for multiplying this is this box method. Your teachers may have taught it to you last year. But basically we're multiplying a trinomial by a binomial, and so I make a 2 by 3 box. And basically this is the area model method. So you'll just find the area of each little box by multiplying. And then you should be able to combine like terms. So those are like terms. Sometimes you get lucky and the like terms are on diagonals. And then we can just write our final answer here. So we should have an x cubed. It looks like my x squareds are canceling. Hopefully yours did also. And then I'll have a minus 12x and then a minus 16, which is what my answer key says too. So yay for me. All right. Last problem today, we're going to go backwards. So here is the polynomial function, and we're going to list its real 0 and its multiplicity. So our first real 0 would be a positive 7, and this is a multiplicity of 1. And again, it's because when we solve for our x-intercepts or our zeros, we just use the zero product property. We set each of our factors equal to 0, and then when we solve it, we would add 7 to both sides, so we'll get a positive 7. That means our other 0 is a -3, and that's a multiplicity of 2. All right, so overall, this is a degree 3 graph. So we would expect it to look something like this, which is a cubic. Okay. Determine whether the graph crosses or touches the x-axis at each x-intercept. Well, it's at 7, 0. Because it's a multiplicity of 1, that means we are going to be crossing. Okay, or going through the x-axis. You could also say it like that. And at -3, 0, because we're a multiplicity of 2, we're going to be bouncing, or you could say touching the x-axis. All right, and finally, find the power function that the graph of f resembles for large values of absolute value of x. This is just a fancy way of asking, like, really, what is this graph going to look like? So I kind of already answered it for you. I said that this was going to be a degree 3, which is a cubic. So what I'm looking for is just f of x equals x cubed, but generally what your book also wants is the coefficient, because the coefficient tells us that we have a stretch here in this case, which is going to change the shape of this graph. So we would want a 3x cubed. So basically this is the most general form of the graph without any of the shifts that are actually going on in this situation. Okay, so that's it. Hopefully you enjoyed your cameo today by Penny. I hope she brought some joy to your day and that you enjoyed this short pre-calc lesson. Have a good day. Bye.